Hello and welcome to the next part of the SummerAcademy. This time it's our home turf. It's about static code analysis. By the way, if you like what you see, make sure to subscribe. Just to make sure we're talking about the same thing here. Static code analysis means we are analyzing the code. We don't run or execute the program yet. It might not even compile yet. So we are just based on the source code. The static code analysis can work on different layers, so to say, of abstractions, and I have some of them here. Let me go through each of them. The topmost layer is the textual layer. Here we treat the application or the source code as a sequence of characters. And as such, we can already use text tools, so we can search for illegal function names and stuff like that. Obviously, it's not very smart, but it's already very helpful. The next one is actually the syntactical layer. Here we understand the syntax of the development language. We know what is an expression and what might be a variable, and we can point out things like typo errors quite easily here. The next layer is the grammar layer. Here we understand the grammar of the development language. So we understand the sequence of expressions that is actually allowed or not allowed. And we can point out where you are outside of the grammar of the language and the language won't work in this regard. The next layer, data flow layer, is where we actually talk about how data is flowing through your application. To unlock this layer, we actually need to transform your source code into what is called an intermediate representation, and I will talk about this a bit later. In the data flow, we can now follow the data through your application. So for example, if external data comes in and you're using this data within a function to prepare, for example, a SQL query or so, this is a typical entry point for SQL injections, and you should treat that data before you use it. That is called tainted data analysis, and this is based on data flow. Next, we have the control flow. Here we are literally looking on the different ways that your application can be executed. And we are comparing these different ways. And with this, we can find out if variables are wrongly initialized and might be dereferenced as null values, for example. This is possible by using control flow and see how the different ways your application can take through the source code. The next layer is the algorithmic layer. And what we do here is we are looking into the intermediate representation, and we are trying to find out what kind of algorithm is literally underlying this. So typical loop algorithms that you have when you're iterating through things. What we can do here is we can try to optimize things and try to find out if the way you are implementing it can actually be more optimized by unrolling the loops and stuff like that. And the lowest layer is actually like the queen of all of them. Here we are trying to find out what was the intention of the developer. So what was originally your idea when you did this, and how is it represented in code? And does the intention that you have and the representation in code, does this compare to each other? A very nice example on this is the typical issue that you have in JavaScript when you have the double equal versus the triple equals or the single equal. The intention of you using a single equal in an if statement is probably not what you intended to do there. So probably you wanted to use a double equal or triple equal, and this is something that we can find out, and we can, so to say, point out that your intention and what you developed here is probably not the same thing. This is a very easy example. Obviously, you can do much more if you have an intermediate representation and you have lots of training data at your hand. We talked a lot about intermediate representations, and I promised you some examples, and here they are. On the outmost left side, you see what is called an abstract syntax tree. It is taking the source code and compiling it into a tree of syntax elements. It's quite simple. It's done in every compiler or every interpreter. And you find a lot of good examples on the internet that takes JavaScript and actually compiles it into abstract syntax tree. In the middle, we have a control flow graph, and this is literally taking your application and compiling it into a graph again that shows how possible control flow are through the application. And a very obvious use case for this is every code that cannot be reached within this control flow graph is obviously dead code. It cannot be reached with the execution, so you can literally get rid of it. And on the outmost right side, you see what is called an event graph. It's literally what we are using within DeepCode. It has the upside that it compiles a lot of information into this graph, and we can compare these graphs, so different changes that you're doing in the code. We can simply do an event graph for before the change and after the change and comparing them, and it gives us a lot of information how the control flow is working, how data flow is working. So the event graph gives us a lot of information in one graph. So let us make a concrete example, and I took this from a tool called Infer. What you see here is we have a series of function calls, and we start with the topmost function, which is called feed item selected. And as you can see, during the next line, we are generating a feed object, and it's literally done by calling the select feed by ID function below. So now we are jumping into the select feed by ID function. And as you can see, we are initializing some internal variables. So feed object out is null, cursor C is null. And then we go in a try finally sequence. And in the try, we are making a database query, and we are then calling the move to first. And this all is nice, but what happens if the database query actually results in an empty result set? So we are getting an empty result set back. If we then go to move to first, this will actually give us a falsy result. Move to first cannot be executed because there is no first. Then out equals get feed object is actually not initialized. So out will not be assigned. We will go into finally, we will execute the finally. C is not null, so it will be closed. Everything is nice. But the problem with this is, what is out now? Out is still what the initialization was, which is null. So we are returning a null. And feed object is now used to call another function, which is feed item selected. And as you can see, feed item selected calls feed object.getURL. But what happens if feed object is null? Correct, we will have a firework, because we have a null dereference. The application will probably crash. What you've seen here is a data flow analysis, and we are literally looking at how the data flows through the application. And sometimes it's no data, it's a null. So how can we solve this issue now? Well, one way of doing it is we are asking the developer to do annotations. So as you can see here, we start off with a normal, it's a Java function in that regard, and we are adding annotations. We're saying, hey, we are expecting object X not to be null, and then the system can literally follow it and say, hey, the intention of the developer was actually that this is not null. If it is null, we have a problem here, we can flag it. That is nice, but it actually asks a lot of work from the developer. You need to do a lot of annotations, and obviously also the annotations need to be correct. So the annotation needs to reflect your intention in that regard. So maybe there is even a better way of doing it. And there is a better way. The layers that I showed you, the most interesting layers, are actually based on what is called symbolic AI. So we have a set of rules that we are applying to our source code to find possible problems there. But what is symbolic AI? There are two major schools in AI, symbolic and sub-symbolic. In the symbolic world, what we have is we are trying to compile facts. And then, based on these facts, we're using rules to solve questions we are asking to the system. If you are thinking prologue here, you are pretty right. Sub-symbolic AI is literally machine learning. So what we are doing is we are having a lot of input data, and we are training a machine to find patterns within the input data so that it gives us the same response that we are expecting it to give us. And so if we expose it to unseen data before, the machine can do a judgment and can give us its judgment based on the previous training it had. And as you can see in the 2000s and 2010s, sub-symbolic AI, due to the now available big machines, big data, was actually gaining a lot of traction. And this is what we see today. This is when we're talking about AI, most people talk about sub-symbolic AI or machine learning. As you can imagine, symbolic AI and sub-symbolic AI both have their advantages and disadvantages. So symbolic AI is based on explicit symbolic programming, inference, search algorithms. It uses AI programming languages such as Prolog. It's rules, ontologies, plans, goals. This is symbolic AI. Sub-symbolic AI or machine learning is Bayesian learning, deep learning, connectionism, neural net backdrop, so the typical algorithms we know of machine learning, SVM and all of these things. This is what sub-symbolic AI is all about. In the symbolic AI field, it is used in introspection. It is easier to debug, it can explain itself, it's easier to control, it doesn't use big data so much, and it's easier to explain people's thought in it. It's better for abstract problems. The sub-symbolic AI or machine learning is more robust against noise. It has a better performance, it's less knowledge upfront because it builds its knowledge based on the training data. It's easier to scale up. Big data is the key word here because it needs that to be trained. It's useful as it is connected to neuroscience. So neural networks obviously are connected to neuroscience. And it's better for perceptual problems. But what if we combine the two now? And this is exactly what DeepCode is doing. So we are using, on the one side, vast amount of open source repos and the changes in these repos within a machine learning algorithm to extract possible new rules for our symbolic engine that we have. This is combined in a process that we called augmented AI because there is an engineer that is sitting on top and is controlling the whole process. But in the end, it is combination of sub-symbolic, so machine learning, and symbolic AI in one machine. And this is what modern static code analysis tools are all about. I hope I got you interested in what modern static code analysis tools can actually do for you. So go to deepcode.ai and either use one of our test repositories or scan your own repository and see what results you get and how the system actually argues on why it finds these results and gives you example cases how to solve the problem right away. This was it for static code analysis. Obviously, we have a lot of resources online on how DeepCode is working, how the nitty-gritty details of the engine are. So if you're interested, make sure you check this out. The next part of it will be unit tests. See you then.